All right, folks, great to see everybody. We'll go ahead and get started today. I'll leave the lights off for a minute. So we'll have a short lecture. That's what the class has spoken, according to our vote. So most people wanted sort of a small lecture, so we're going to do one game programming pattern. I want to at least introduce the idea of tagging memory and what that is. I think a lot of people sort of had interest in that in the previous lecture. And then I'm going to try to check in with every team just to get a report on how things are going progress-wise. So sort of sit near your teams if you aren't already, and we'll kind of keep powering through. Again, just to see what the schedule is, we'll have one more lecture that'll sort of be of this flavor of short work, some sort of special topic, likely a game programming pattern that we haven't touched on yet. We've actually almost seen all of them from the Nystrom text, which is kind of cool to have that coverage. And then next Wednesday will just be a work day, and I'll want to check in with everybody before our final sort of science fair of showing off our final projects. So we're almost there. But just focusing on the final project now, getting all that out. Any questions on course logistics?
So there's no more labs?
No more labs, yep. That's, if I push anything out, it'll just be sort of support code. So for today, if folks were super interested in the threading stuff, Evan Jones is a software developer who does some pretty interesting work. And has a pretty good starter set of just how to implement your own thread library on Linux. So this is sort of worth reading through just to see how do you get registers, how do you save them, how do you manually swap contexts. So this will get you close to at least thinking about the fiber system and some of those things that we talked about on Wednesday. So this could be sort of a take-home exercise. Again, the focus is going to be final projects and pushing there, though. But I think this was really cool. Other questions on logistics? I'll check off folks' lab, their Unity lab, if they didn't get that checked off last time, but I think I got most everybody otherwise. Alrighty. Alright, so that's the warm-up. I literally am sweating after being outside for 5 minutes here. So I know it's a nice day, so we'll just get started. We're recording. Again, push on final projects, lab check off, working with your teams today. The in-class activity at the end of the lecture will just be sort of giving me a little write-up of what did you work on with your team, just to give you some push for forward progress. Okay, so last lecture we talked about concurrency and parallelism, starting with some stuff on architecture, so reviewing Moore's law, Dennard's law, why we had to move to multi-core in general. The answer is sort of physical limitations. Then we talked about what a thread is, but maybe in a little bit different context of what you learned in system, thinking more about threads, about just how much information are they carrying with them. Registers, call stack, thread ID, that sort of information, and can we get rid of it, which is really what the game engine study part was about. Let's see, then we saw some of the C++ thread examples, just on the sort of standard library built into modern C++ 11 and beyond. And this is going to be a trend for C++ programmers to keep pushing on this. For folks who have done Unity and C# stuff, the big talk with C++ is adding coroutines to their sort of thread library. So just launching some thread that'll run for a little bit and then return. So some cool stuff going on in the sort of C++ concurrency world. And then some other cool things like atomics, where you don't really have to worry about the locking. It's built in for you. Okay, so just a little review on that. Then again, the game engine study, we looked at two systems primarily, Naughty Dog and Destiny Engine, and how they implemented job systems using something called fibers. Naughty Dog, more sort of interested in how do I build a really simple, easy to use job system where I can launch threads and then see the bottlenecks. So that was their sort of profiling tool over here. And Destiny, a little bit more interested in how can I see different data dependencies in sort of this job graph, and then actually like formally prove like something's dependent on another thing, and how to sort of arrange their data. Yeah.
I was just curious about the fibers.
Mm-hmm.
Is that simply that they were putting threads on a thread kind of thing?
Yep. Yeah. So yeah, fiber is an even more lightweight thread, and they're just sort of managing it themselves, meaning how they swap the call stack and the registers. And in some cases, since they forced a thread to just stay in one core, that was another boost, so it didn't have to sort of move around. Data that stayed in that CPU's cache got to just stay there. So that was really one of the big wins from their system. In fact, I think if they just said, hey, we're just going to use regular threads but sort of lock them into one CPU, I think that would have been just a pretty significant boost in itself. But then they took it one step further and said, well, fiber is just going to be a little bit more lightweight, which was cool. But definitely, that's something worth revisiting. Maybe even after the semester. If someone implements a job system in their engine, that'll be super cool. But sort of revisiting those talks. I've watched that talk probably 3 times, and every time I watch it, I understand like 1 or 2 more cool tricks. So I really like those talks. That's how you know it's a good one. Any questions about the other stuff from last time? Cool. All right. So today, sort of the brief topic of memory, sort of one of the finite resources. We've talked about memory a little bit in the context of allocators, different types of allocators that could implement, and why it's just expensive in general allocating memory. You have to context switch, you have to go to the heap, find what memory is free. Potentially there's some fragmentation if you're allocating blocks that are too big, or even internal fragmentation. So that's where you sort of get a lot of your performance penalty or lose performance just on requesting memory during runtime. Right? Anytime you do new or malloc in your systems. So that's one cost. Then of course newer languages like Java, C# came along and said, hey, managing memory, it's also error prone, so we're going to do it for you. And they introduced garbage collection. Well, that has another cost to it, okay? Because then the system's automatically saying, well, what memory aren't you using? And occasionally has to reclaim that memory. Essentially stops the world and says, hey, we're going to collect up this memory. Okay, so those are costs. So anything we can do to sort of aid performance when allocating memory is a good thing, especially in games. And today's pattern is really the mantra or maybe all-encompassing theme of game development that just says allocate memory up front as much as you can and then try not to allocate ever again. Okay. So with that, I want to introduce the object pool game programming pattern and what this is. So in a sentence from Nystrom, he says, the object pool is a pattern to improve performance and memory use by reusing objects from a fixed pool instead of allocating and freeing them individually. Okay. So the real key here, just on term, is you have a fixed pool of memory, something that you've allocated, again, up front. While your game's in the loading screen, you just say, this is how much memory I'll need. And that's where you're going to generate your objects from. Okay, so you don't have to go into the system and ask for memory again. Okay, so with that idea of what an object pool is, there's two claims that I see in this sentence that we are sort of going to improve performance and memory usage, and how do we do that with a memory pool? That's what I want to look at briefly here. And this really is sort of a low-hanging fruit. This would be something in your projects you could get away with doing, right? Especially in a tile map system. Maybe I'll ask about that in a little bit. But object pool is kind of a low-hanging fruit. So let's see what it is. Okay, so how do we implement object pool, the pattern? We define a pool class that maintains a collection of reusable objects. Okay, so it's just some collection of things. Each object supports an in-use query to tell if it's currently alive or being used. When the pool is initialized, it creates the entire collection of objects up front, usually in a single continuous allocation. So that's sort of a hint to our data structure. And it initializes them all to the not in use state. Okay. So what this sounds to me like is it's just making a giant array of things. Okay. And there's some extra attribute saying, is this being used or not? Okay. And then you have a pool of those things you can grab from. Okay. Some examples of when this can be useful to use an object pool. Typically, if you have lots of objects that are created and destroyed, that's where this pattern shows up. So examples I could think of in gaming, particle systems, that'll be sort of the running example. You know, your explosions are happening or little spark effects, right? You're creating lots of those little particles and destroying them. Any like sort of projectiles, destructible objects, maybe other objects that respawn in the games, collectible things, power-ups. These are all things that can be sort of reused, right? Because they're often being created and destroyed. If you're looking through your code right now and trying to think of what could be a candidate for an object pool, just look for anywhere in your main loop where you're doing malloc and free or new and delete. That's probably a candidate for an object pool. Maybe as a rough guideline. Okay, so any of these things, right? So on the right, game, right, here's projectiles, so any of these sort of green blasts, probably some object that's being created, but it looks like at most I'm only firing maybe 3 at a given time, right? So I can sort of recycle these objects. Okay, that'll be a thing. This particle simulation, I guess the GIF's not running on this side, but you just have to tap it and then it runs. If you notice, so there's a bunch of particles, right, and they sort of fade away and dissolve in kind of this pretty effect. But if you look at the actual number of particles here, it's fixed, just how many there are in the system. They're sort of respawning, moving in a different position, right? We're not creating a new particle over and over and over again. Here, wait, let's see. Wow. So that's the idea. Okay. So what's it look like in the code if you're going to implement this? Here is a particle system. The example. So you would have something like a particle. Here it has frames left. How many frames in the game is that particle going to live? Could be the lifetime or a time for it. Then you have whatever your object's regular attributes are. In the case of a particle, it's things like its position, its velocity, how it's moving around. Right? These are just your regular game objects, things it has. And then the key is this sort of in-use attribute. Okay, so a particle is in use if it has more than 0 frames left in its lifetime. That is, there's more time to render and see that particle. Then it's in use, decrement its frames, and move x and y based off its velocity. Okay, so that's a basic particle, but the new thing we're introducing is just, is it in use or not? Or in the particle example, you can just think of, is it alive or is it faded away? Okay. Everyone clear on this one? This is what a particle is defined as. All right, so let's add in the pooling mechanism in the particle pool. Okay, so if you have your object pool, in this case it's specifically for managing particles or a particle system. I have a way, or I have some array here of particles, and I have a pool size, in this case 100. So at most this game or particle system supports 100 particles at once, okay? Or at least in each pool. Okay, so I've sort of just, at runtime allocated this array here to a size of 100, and that's it. Okay, so we're stuck with that. And then when I need to loop through these particles, I can animate for however big the pool size is. Okay, so if I rewind to this example, my pool size is 7,687 particles, and that's it. Okay. Okay, and then in our then when we create a particle, we're just finding an available slot that's not in use in this array. Okay, so I have a loop here that's going to look through my entire pool size. So it's looking through this data here to see which of these particles are in use or not. If it's not in use, then I create, this is the create function here, a new particle at whatever position x, y, however long it's going to go, what other attributes. Okay, that's what I'm populating. I'm just changing the data of some object that already exists in this array. Okay. Does that idea make sense? Yeah, folks. Cool. All right. So, I will argue with this strategy, this pooling strategy, this sort of solves two of our problems regarding performance and memory. It fixes the memory problem in a sense that we've just allocated everything up front, right? So we know exactly how many things we're going to need. There's no fragmentation if I'm sort of allocating particles and then some other game object and then a third type of game object. It's just all my particles are there, exactly as much memory as I need, and they're contiguous, which gives us some data locality, right? Some cache friendliness, and that's good for performance. Right? In general, arrays good for performance. Okay, so that's the pooling strategy. All right. Questions, comments on this? Yeah. All right, cool. So let me give a few just design decisions to think about with pooling. So the first is, how big do you make your initial pool? If I had said particle pool 1 million, well, remember, you're allocating all of that up front. From your system, you're requesting that many particles. So is that too big? Is that too small? You might not know. So ideally, you might have to profile your code, test, have some sort of heuristic to figure out what size to initialize things. Okay. The second thing is, can you do something better than an array for maintaining what's in use? Okay, so here again, if my pool size for particles is 1 million, how long does it take to run this algorithm here with the loop? What's the complexity? Starting from 0 to the pool size, big O of n, right? Every time we have to iterate through this entire collection to find some particle. That could be expensive, right? So maybe we can even have a better strategy for just searching and finding empty objects that we can reuse. So typically, one strategy is to have what's called a free list. This is how a lot of your memory allocators work. They look for some block of memory that's free, not in use, to just point to the next available free thing. Simple fix for this is just have an extra pointer that points to the next particle that's free, or maybe an integer into that list. Okay. So you can get a little bit wilder with some of these structures, but that might be one simple fix here. then you just have constant time lookup to grab the next particle. And then 3 is, it might be sort of annoying or add a lot of code to have a particle pool, a game object pool, a sound pool. So if you can have some more generic object type for your pool, this might help with your sort of implementing this pattern for different types of objects. So here is an example provided of just a template object pool for the same thing. Now you might have different things for creating or updating what's in your pool, but that's just one thing to think about. Okay. So the question I wanted to ask is, could anyone see in your platformers where they might be able to use this pattern? Could you give me examples of like game objects or objects you use? Enemies? Yeah.
For the tiles?
The tiles, yeah, because we have a fixed amount of the tiles that we need to put on. And we know exactly how big it is. Enemies get destroyed and respawn. Tiles, the data just changes. So, right, any collectible things you have, those are all candidates. You could go back. Awesome. All right. Lingering thoughts or questions on object pools, then I'll move to the next few topics. Yeah.
So for the free list, do you have thoughts on showing us that?
Yeah, depending on how it's implemented, it could just be as simple as the particles would just sort of have a pointer to the next available slot. Could be just within the pool, just an index into what the last not in use thing was, depending on if things sort of die in order, I guess. But yeah, essentially you just have pointers to the first available thing in this list.
And does C++ have similar, is the garbage collection very similar like Java, or is it, you have to define a lot more?
So C++, right, we have to do the management ourselves with new and delete. There are things like, for instance, like smart pointers and stuff, which sort of clean themselves up. But yeah, otherwise we have to manage things. And with Java, there's many different garbage collectors you can use. I don't know if there's any like built-in pooling ones or how well it does actually of reusing objects. There's some collectors that'll do that, right? If it notices you're making a lot of particles, maybe don't delete particles right away. Reuse that object. What else? Anything else on this? Cool. So I think this is a cool pattern. It's something that you can implement in your projects and see a difference. Okay, so a little, if you want to see a little example, so there's sort of the Unity video. That one's 49 minutes, so we're not going to watch it. So here's a 1 minute, let's see, example here. So here's just a little game. They've got a little profiler here. Tiny text, but I'll just tell you how many entities there are. Everybody can read this, right? So there's 2 things here. Here's sort of some lasers being shot off at the top. 37 or so entities. Right? So they're going to reboot their game. And I think you're going to see the number 9 or something here that's fixed. So that's the idea. Right, so it's going to be reusing the same particle effect over and over and over. If I pause it, yeah, it's 9 here. So they saved about 20 or so game objects. With the other one, when they fired the projectile, it just went off and off and off and off, and eventually its lifetime ran out. But it was just constantly creating new objects. So this was a better system. Okay. Again, if you want to see the Unity one's pretty good. 49 minutes. I think in some of the early Unity tutorials, maybe it's the space shooter or something, there's also a 5-minute version of doing the pooling system.
So does Unity guarantee that if we set up a script with references to prefabs, and then use them and I guess not destroy them, but just save them or whatever, but it'll always maintain that memory for us.
Yeah, because I think the way it's set up in Unity with the object pool, as long as some object has a reference to it, it can't reclaim it. So I think when you set it up, that guarantee should hold.
And I guess even if we did destroy it, since we have the reference to the prefab and we initialize it again, we should just use the same memory.
Yeah, as long as there's still some reference back to it, it shouldn't be reclaimed. That would be like a, yeah, that would be fine. Other questions on this stuff? Cool. All right, cool. I just want to give a few, maybe these are more keywords for your interest, but this idea of memory tagging. And this is sort of getting into the profiling of your game engines. But there's a nice talk on memory tagging. This is from CQPCon this past year, mostly on memory safety. The idea being that when you do things like allocate memory on the heap here, use it, delete it, and then if you try to use it later, that causes a problem, right? This is a use after freeing your memory. Okay, we can't do that, right? Because our system might have reclaimed it for something. And sometimes these errors are kind of obvious. Like I'd say this is a pretty obvious one. You could probably catch this looking at it. But sometimes it's not as obvious when you're creating objects. Oh, I guess I don't have another example. Strings are sort of notorious. Strings, string view. Sometimes when you create objects, other temporaries will be created. And if you sort of reference those, it's not as obvious if they've been reclaimed or not, okay, depending on what library you're using. So we have tools like Valgrind that help catch some of these memory errors if you're on Linux. If you're on pretty much any other tool that supports the Clang compilers, Clang++ has something called an address sanitizer. And what it basically does is every time you allocate memory, is it makes another like copy or shadow copy of that memory, and make sure that nothing else points to it ever if it's been freed. Okay. So there's a little usage example. This could be something to sort of play with today. If you want to run Valgrind or one of these sanitizers, here's the sort of magic command line in Stack Overflow. fsanitize address, and it'll tell you if you have these memory errors on your program. So that's sort of one idea. You have every byte of your memory is sort of shadowed, and you can check for these errors. Another way to sort of think about tagging memory, and this is sort of more in the game engine design, was there's a sort of nice talk from Nicholas Fleury. I think he is at Ubisoft on just how they use these tools in their AAA games. But the basic idea is just to say, well, every time you use new or are allocating memory, just write your own wrapper over the new function. So in this case, they called it UBnew for Ubisoft. The object that they're allocating, what system it's coming from, and then a string to just give sort of as debug information of what was allocated here. That's kind of a nice way then. So what they did is they sort of like dumped out these logs to say, okay, FX manager is making 400 particles in this subsystem. Okay, so the insight then is, well, if they're using object pools, make a pool at least 400 or whatever. So that's the idea of tagging your memory, right? You can just wrap the new function in some other function in this way. Okay. Let's see, what else do I want to say? This is also how you sort of get these visualizations from the Naughty Dog system, right? If you're just trying to figure out, we talked about what some of these colors meant. I think I showed one slide where there was like green meant the rendering engine and then red meant the gameplay system or whatever. That's how you can sort of retrieve some of this information in debug. Tagging your memory, or at least in the Naughty Dog system, is more tagging each function and associating it with some system, particle system, effects manager, etc. Okay. Does that idea make sense to folks? I can sort of wrap these functions, just make a new helper function, UB_new or whatever your game's called, and it can call the new and the regular allocator, but have it do a little bit of logging first. Sort of a cheap way to do it. Okay, what else do I say? Some of this wrapping of objects when you're creating them, it might be a little bit annoying to do this for every single thing in your game when you create an object. So there are instrumentation tools to help with this. And the one big one, unfortunately not free, but it's the probably best known one in the industry, is called telemetry. Telemetry is the other key term you'll hear instead of profiling your games. So profiling or telemetry. And this is from Rad Game Tools. And they've got some instrumentation that wraps all of your memory accesses, all of your function calls, and gives you sort of a nice visual display. So I just want to show a minute of that. I'll sort of narrate it as it goes. So here's their stuff. And right away, whoops, let me pause it here. You can see it's profiling what subsystem it came from. Your physics engine, render, main, and these are just little wrappers around things. These are all the function calls from the system, then they're zooming in to see what those calls were. This thing calls that, calls that, calls that, which calls a whole bunch of things. How much time, how many cycles you spent in there. So these tools can be pretty powerful. There's all of your calls, how much time you spent in each of these systems. So it's a good way to see what's going on in your engine and what order things are happening. And again, thinking about object pools, how much memory you're allocating in these different functions. So there's a quick, so you can actually see it has notes like, what are the memory allocations? Well, in this subsystem, 0, apparently. Must be pretty efficient. And again, I can see some of the things like what's going on in each core, the context switches, so you can see what thread's running. So this is just a cool tool I want to bring to people's attention, that they exist and you can use them. The sort of free ones that you could use are like perf on Linux. Xcode has some built-in tools. I forget what their profiler is called. Windows has something called Very Sleepy that's pretty handy for profiling, and so on. Okay, so those are the telemetry or profiling tools. All right. Any questions on this idea or of memory tagging? Either just wrapping your functions manually or with some help of a tool. And then there's this idea of address sanitizers, which can help you with some of these debugging things if you're having memory problems. Okay. All right. So 2 feeds. That's what I've got for you guys in sort of the mini lecture. So the next thing I'll ask you folks to do, I'll make sure that in-class activity is open. But what it is it's just going to be for the rest of class to meet with your team, or if you're working individually, just set up your system. And then by the end of class, just kind of write about your team name and what you accomplished today. I'm going to try to visit everyone individually in their team and just check in or help out. And that's the day. That's the game plan.